All right, good afternoon, everybody. Welcome to lecture 23. So we're going to continue our discussion on Kalman filters, and I'll start by sharing my screen. So I'm looking for a brave soul to answer some questions about what we learned last week in lecture 22. So it's going to be not super heavy on the math, but I just want to make sure that everybody gets the idea. Anybody feeling particularly boisterous today? Oh, maybe not. Going once, going twice. Anybody have any thoughts on Kalman filters, or is everybody's brain still stuck on homework 4?
I don't think it's particularly fair, but I can answer.
Okay, so I know you have a greater familiarity with Kalman filters than some other folks. So, but I appreciate that. That's good. So, really quickly, what we learned about last time was a Kalman filter. What do Kalman filters do in like the plainest explanation that you can come up with?
So, I mean, basically the first sentence, it's an optimal state space based model based estimator. They balance measurements, like a measurement model versus a propagation model.
Great. Yeah, that's pretty much it. So there at all times, you've got this kind of computer algorithm running that is making decisions between, do I trust my physics model or do I trust my measurement model? And so there's two main steps to a Kalman filter. And do you remember those, Renee?
Yes,
Yeah.
propagate and update, or a priori and a posteriori, if you
Yeah,
want to
there's
use the
there's a
Latin.
couple of different, yeah. I prefer the propagate and update, but only because I can pronounce those comfortably. But other there's perfectly valid to say the other ones. So then, just to keep hammering that the nail on the head, what is propagate and what is update?
So propagating is when you push your physics model forward. So your x dot equals ax plus bu or something like that. And
Mhm.
update is when you correct based on your measurements that you receive.
Great, excellent. That all sounds fantastic. So last question, you're batting 1,000 right now. Keep it up. Last lecture, did we focus on the propagate step or the update step?
Propagate.
Good, excellent, very good. Oh, you're paying fantastic attention. I appreciate you, Renee. All right, you can let your guard down now because we're done. I'm done calling people out to answer questions for a little bit. I really appreciate you assisting me on that. So yeah, everything that Renee said was 100% correct. So we learned about Kalman filters. So a couple of weeks ago, I was at a Johnson Space Center outreach event, and we were talking to K through 12 students in the Clear Lake area. And there was a student who seemed particularly on top of things, who started asking me questions. And this guy was like a junior in high school. I was blown away. Like I had never heard of a Kalman filter until like late undergrad, early grad school. And he didn't use the words Kalman filter, but we got talking about navigation because that's what I do, and we started talking about navigating in space. And he said, couldn't you do some sort of dead reckoning where you thought you knew where you were a few minutes ago and you just used physics to update? And before I could answer him, he thought, well, you'd probably also need to take into account your measurements. So, like, if you're taking measurements, but you also kind of know where you are, is there like some computer program that just figures that all out? And I was absolutely floored. Like, this I was blown away. And I wound up giving him my business card and told him to reach out for an internship when he's old enough, because like that's exactly the right way to be thinking as a navigator. Is like, isn't there some computer program that you can be running that is constantly keeping track of where you think you are because of your gut or your internal physics model, and where you think you are because of external measurements, and ultimately needing to make a judgment call with each next measurement that comes in. Do we trust it or don't we? But unfortunately, it's not even a binary decision. It's not do we trust it or don't we? It's when we use that measurement to update our state location, how much do we trust the measurement versus how much do we trust the physics model? So it's kind of like a slider more so than it is a more so than just like a light switch that you turn on and off. It's more like a dimmer switch. So hopefully that all makes sense. There's really not that much in the way of pretty pictures. Well, there's no pretty pictures if I'm drawing them, but there's not much in the way of illustrations throughout our Kalman filter lectures. But this is kind of the best that we've got. And I'm trying to depict that you've got these different phases of flight. So whenever you're taking a measurement with your sensor, and that could be a camera, that could be an antenna, could be whatever you like, you're in a measurement kind of phase, which is really an instant in time when you take the measurement. And then you're drifting between measurements, and in between those, you are propagating. So you've got your update step and your propagate step, and you update step and your propagate step. And your uncertainty grows. It kind of creates this like blunderbuss barrel shape slowly over time. Your uncertainty is going to get worse and worse and worse. And then it's tugged back in by your measurement, right? And that's the idea. And so you get this kind of almost like a sawtooth pattern of uncertainty as a function of time. And of course, it's symmetric, right? Because if this is a plot, for example, of your position on the x-axis, when you're uncertain in both directions, right? Is it positive or negative? That sort of thing. And so measurement noise is one of our tuning parameters, right? We have a model for the noise in our measurements. And that is one of our knobs that we can tune to make sure that the filter works properly and to say that we're giving the proper amount of trust to each new measurement. Whereas process noise kind of is where we insert our uncertainty in our physics model. And so you can end up in these states where if you have tuned your Kalman filter wrong, if your process noise is way too low and your measurement noise is way too high, you basically just don't trust your sensor anymore, and the filter is said to be smug. And that's actually the technical term. Whereas if your process noise is way too high and your measurement noise is way too low, this is the other end of the Goldilocks problem. Now you're ignoring your dynamics and you're just passing through each measurement. It's not a Kalman filter at all at that point, right? So what you're trying to do with the Kalman filter is to be the driver on the road trip. We used the road trip metaphor the other day. If you were going on a road trip from Troy, New York to, say, Rochester, New York, and you're driving for about an hour, there's no way you made it to Syracuse in 1 hour. But if your navigator in the seat, who you're not really sure is paying attention or knows how to use Google Maps, insists that you have made it to Syracuse or that you are just a few miles outside, you'll say, absolutely not. I don't trust that at all. I just it goes against my gut, right? And in that moment of saying that the nav update goes against your gut, you are a Kalman filter. That's essentially the idea. So there's two broad steps, right? So there is propagation, which is what we talked about last class. So propagation, if we start with a dynamic model, we need to ultimately be able to update our estimate of the state and then also our covariance or uncertainty in the state. So after a reasonable amount of math, we end up with this red boxed equation for our state propagate equation, right? And then after maybe an unreasonable amount of math, we arrive at this nice and short and sweet equation for the covariance propagation equation. Now, these are the general form, but in reality, if you were actually trying to code this up, you only need to propagate your state and your covariance from the last time step to the next time step. So it's these equations are closer to what you would actually see. And we decided to stop right there. We didn't get quite as far through the notes as I would have liked to, but that's totally fine. We've got about one more page of notes on state and covariance propagation. So today we're going to start with actually a simpler method. So if you weren't a fan of this, there is a simpler, although not necessarily recommended, method of state and covariance propagation. And then we're going to spend the bulk of our time today on update. I want to end maybe not necessarily early, but certainly not late, because I want to give us a reasonable amount of time to talk about homework 4, which is due tomorrow. So if we don't get through all of my notes today, that's fine. We can push it to Monday. The Star Tracker lecture series was pretty rigid in what we were going to cover each day, whereas this one is a little bit more loosey-goosey. I just have a stack of notes I'm trying to get through in whatever length of time that we can. So any questions on lecture 22 before we go back into the fray and start the heavy math on lecture 23, Kalman filters part 2? All right, I'm going to start writing notes then. So we're going to start with state and covariance propagation. Again, so we're getting deja vu, but this is an alternate method. And this is one that my professor, John Christian, referred to as a down and dirty Kalman filter. remember how ridiculous I thought that sounded, so I wrote it down in my course notes. But I want to be clear that while this does work, this is not recommended. So, take this with a grain of salt. This will work, but this is the sort of thing that if you're trying to follow navigation filter best practices, probably not. In future versions of this course, I might even omit this from our discussion, but it doesn't hurt to show you how this works. So the idea here is, instead of using the state transition matrix, which is ultimately what we were trying to accomplish in the last, in lecture 22, you see our equations for P and X have the state transition matrix phi in there a whole bunch. The equations that we're going to be going over today are more in terms of differential equations. And so let me take a look at my notes. Does phi still factor in? No, it does not. So we'll be seeing phi a lot in our equations, but ultimately we'll be seeing a phi a lot throughout the derivation, but our final equations will have no state transition matrix in them today. So we can start. We may also write state, so the state and covariance propagation as differential equations. So we'll start with this. So this should be not news. X dot of t is equal to f of t, x of t plus g of t omega of t, where the first term is the actual physics, and then the second term accounts for noise, and that is process noise, right? If we take the expected value of both sides, we get that the expected value of x dot t is equal to f of t times the expected value of x of t plus g of t times the expected value of omega of t. Now, omega of t is our process noise. It is white noise. It is non-biased, meaning it is zero mean noise. So the expected value of zero mean noise is 0. So this whole second term goes away. And I'm going to follow the notation from yesterday where a state estimate has a little hat on it. So this is to say x dot t is equal to f of t x of t. And that's it. I mean, that's about as simple as it gets. So what you could do if you didn't want to use the state transition matrix is you could just use our kind of first order linear differential equation here. And this is the other state propagation equation. And it's just it. It's just exactly what we would be used to. You could pop this into something like ODE 4.5 or ODE int, and you can use that to integrate your equations of motion, essentially. So you would keep track of your state estimate by saying, well, look, on average, the noise is going to cancel itself out, right? There's no bias to the noise. So we're just going to ignore it completely and propagate the state anyway. All right. And then let's talk about covariance. So once again, covariance is going to be a little bit more complicated. So next, we move on to covariance. All right. So we'll start with P of t. So this is our equation from before, right? It is phi of from t naught to t, p t naught, phi t naught to t transpose, plus the integral from t naught to t of phi t epsilon g epsilon q epsilon g epsilon transpose phi from epsilon to t transpose t epsilon. Right, that's our equation from before. Now what we would like to do is use calculus to find T dot. That's what we're after. So here we go. We'll take the derivative with respect to time of the left-hand side. That's P of T. And time to take some derivatives. Okay, the first term is three things multiplied together. So it should be the derivative of the first times the second times the third plus the first times the derivative of the second times the third plus the first times the second times the derivative of the third. Cool. That's the same thing as a dB plus b dA, or 1d2 plus 2d1 from, calculus. In this case, however, P of T naught is a constant value. It has no derivative. So there's going to be two terms that come out of this. It's going to be phi dot from T naught to T, P of T naught phi from T naught to T transpose, plus phi from T naught to T, P of T naught phi from T naught to T transpose dot. So far, so good. Plus the derivative of that integral that we saw before, which I'm going to get lazy and just not fill in the middle for one step, right? This thing, we need to take the derivative of it. Now you might be saying, oh, well, Paul, don't we just, doesn't the d dt cancel out the integral and then we just get the stuff on the inside? No, I wish. That's not how that works. So actually, we're going to apply something called Leibniz's rule. So Leibniz was the other fellow that figured out calculus around the same time as Sir Isaac Newton. Isaac Newton gets all the credit, and then Leibniz gets to be the fact that you share at a dinner party. It's like, well, actually, Leibniz figured it out. And Leibniz has a rule. So let's see here. Remember, I'm going to try to spell this right. Liebnietz, and then it's apostrophe s because it's possessive. Leibniz's rule. If you've run into this before, I have not run into this before, but the derivative with respect to some value alpha from a, which is a function of alpha, to b, which is a function of alpha, and the inner term is some function of x and alpha dx. Okay, that's kind of what we have here. It's the derivative with respect to time, where time is actually one of the bounds of the integral. It's not the bound of the bottom integral, but it's the bound of the top integral. And then the function that's inside is partially a function of time and partially a function of some other stuff. And then the dx, in this case, it's d epsilon, is not alpha. That's a critical part here. So this can be broken down into three terms. So first it's dB dA times f of b alpha minus dA dB f of a alpha plus the integral from a to b of the derivative with respect to alpha of fx alpha dx. So this is not one of those cases where it's like, you're telling me you haven't seen this before? It's like, no, you probably haven't seen this before, but this is going to be super useful in this exact circumstance. So let's start breaking down this term. The derivative of this integral should break down into three terms now. So therefore, we have d dt of the integral from t naught to t. So we're going to write it all out once. By t epsilon, g epsilon, u epsilon, g epsilon transpose, by t epsilon transpose, d epsilon. All of this, okay, so one term at a time. It's dB dA. So in our case, that would be dt dt naught times the whole interior where we plug in b for x, or in this case, it would be epsilon, right? So we're going to start plugging in t wherever we used to see an epsilon. So this is going to be phi of t and t, okay? G of t, Q of t, G of t transpose, phi of t and t transpose, okay, minus, okay, what's the next thing? It's dA dB, which is going to be dt naught dt times some stuff. And I'm not going to waste your time because this is already 0. So we're just going to skip the second term. Okay. And then the third term is going to be the integral from t naught to t. So we keep the same bounds of integration that we had before, but then it's the derivative with respect to alpha, where in our case, it's the derivative with respect to time of the interior, which is going to be phi, t, and epsilon, g of epsilon, q of epsilon, g of epsilon transpose, phi of t and epsilon transpose, and then close the parentheses, d epsilon. All right, clear as mud. Everything's way better now. It's like, all right, well, one thing at a time. What is the derivative of time with respect to t naught? Well, that's just going to be 1. What is phi acting between some time and the same time? Well, that's going to be the identity matrix. Similarly, this is going to be the identity matrix. So this whole thing becomes GQG transpose. So the first term is a little bit more nice to play with. The second term is 0. Let's look more closely at that third term. So looking more closely at the third term. Apologies for the stray marks here. I used to be so annoyed whenever I had a teacher in school that was working off of like a whiteboard or a blackboard, and they would erase almost everything, but they would leave like 2 stray marks and then get right back to teaching. And I'm like, no, please fix it. And it's like now I'm on the other side of it, and I'm just like in a hurry to get through the notes, and I see it both ways now. But anyway, let me know if I'm doing something that's like overtly annoying. Next is, okay, so this last term. So we want the derivative of all this stuff. Okay, great. Well, so in that case, wouldn't it be the derivative of the first thing times everything else, plus the first thing times the derivative of the second thing times everything else, plus it'd be 5 terms, right? That's the idea. Fortunately, g, q, and g again are not functions of time. So there's only going to be 2 terms. It's going to be the derivative of that first phi times everything else, and then everything else times the derivative of that second phi. So let's split that up then. So this is, there's no equation here. This is just going to be a single expression. The integral from t naught to t of, opening up a big old bracket, phi dot t and epsilon, g of epsilon, q of epsilon, g of epsilon transpose, phi from epsilon to t transpose, plus phi from epsilon to t, g of epsilon, q of epsilon, g of epsilon transpose, phi from epsilon to t transpose dot d epsilon. That's the third term. And so at this point, you might be thinking, gosh, Paul, this is worse than we started. It's like, well, bear with me. Things are actually going to get pretty snazzy in a minute here. So we're going to recall, this, that phi dot is equal to f times phi. And by that same logic, then phi dot transpose is equal to what? Well, it would be phi transpose f transpose. Okay. Put a little ampersand there. So we can substitute. All right. So we don't want to forget the first 2 terms. So gonna just scroll up for a second here. The derivative of p is this term plus this term plus this term plus this term. So we've kind of been dropping breadcrumbs for a while now. Let's bring everything back together. So p dot of t is f of t phi, and then we have phi of t and t naught transpose. There's our first term, plus phi of t naught to t of t naught, phi of t naught to t transpose, f transpose. There's our first two terms, plus g of t, q of t, g of t transpose. Okay? And then finally we have f of t times the integral from t naught to t of, okay, just making sure I have my stuff straight here. So phi, t and epsilon, g of epsilon, q of epsilon, g of epsilon transpose, phi of t and epsilon transpose, d epsilon, plus, I'm going to try to fit this on one page here, plus that same integral. So integral t naught to t, and try to squeeze this in, phi t epsilon, g of epsilon, q of epsilon, g of epsilon transpose, phi t epsilon transpose d epsilon times f of t transpose. Okay, these five terms are p dot of t. All right, it's not so bad. So we can now combine like terms. Or I should say, let's combine terms according to f of t. What do I mean by that? The first term is f of t times some stuff, and then the fourth term is f of t times some stuff. And the second term is some stuff times f of t transpose, and the fifth term is some stuff times f of t transpose. So what we're going to do is we're going to have f of t times first term, fourth term, plus second term, fifth term, f of t transpose, plus this. So we're just going to group this into 3 terms total. So it's going to get a little bit prettier, maybe not. We'll see. Let me know if I'm going too fast and I need to scroll up, by the way. So this becomes p dot of t is equal to f of t times, huge square bracket there, and the first term would be phi of t, t naught, e of t naught, phi of t, t naught transpose, and then the fourth term is this integral, right? Integral from t naught to t. Bet you're getting tired of writing this. Now we're almost done. Go g transpose, phi from epsilon to t transpose, d epsilon. Okay. And then we're going to combine the second and the fifth terms. So we're going to say plus, and this is going to be the exact same thing, right? Phi t naught. This is where I could use Microsoft OneNote's copy paste tool, but those of you that are writing on ink don't have that. So in solidarity, I'm going to write the whole thing again. Q G transpose, phi transpose. There we are. And that's times f of t transpose. And then our final term is G Q G transpose. Actually, I found a mistake in my notes. So this is a good point to pause, get caught up. All right, so this is where things get a lot better in a real hurry. This whole term here can be simplified. Because what is that? Is that not just P of T. That's what we started with. So our whole equation all of a sudden gets a lot friendlier in a hurry. It becomes this. P dot of T is F of T, P of T, plus P of T, F of T transpose, plus G, Q, G transpose. And that's a lot better. And we're not writing that dumb integral again and again and again. So this is our alternate form, our differential equation form of our covariance propagation. Covariance propagation. All right, because what we have here is a first order differential equation. Something times P plus P times something plus something equals P dot is essentially what we're left with. So if you were going to try to implement this in a real filter, this would be what I would call the ODE 4-5 method. And so to run in ODE 4-5 or ODE int or some other solver, you need to vectorize. What do I mean by that? Well, ODE 4-5 is expecting a state vector that it is constantly updating. And so what you would do is your state vector would be your actual state plus P split up into columns and then stacked is the idea. So you would take P, which is a matrix, turn it into a column, and then that would be the thing that gets passed into ODE 4-5. And then each step of the solver in ODE 4-5 would need to reform P into a matrix, do this equation, and then reform it back into a vector and use that to propagate. That's the idea. So it's a little bit of extra work. Now, here's the problem, right? This method is, well, it kind of comes back to what we were talking about before, right? So we learned in the first homework assignment that ODE 4-5 is not good enough for orbit propagation, right? Your small numerical errors will start to stack up, and over a couple of days, or certainly over a couple of weeks or months, those will become an intolerably large error source. And so because this is the ODE 4-5 method when compared to kind of the precise analytic method that we saw before, this one comes with kind of like a, I'm going to grumble a little bit if I see people doing this. This is definitely not the preferred way, but it will work, reasonably well enough for short periods of time. So this comes with a caveat. The preferred method is definitely the one that we learned back in lecture 22. So any questions on that? Otherwise, we are all done talking about state propagation, and the rest of it is measurement updates. Feeling good so far? All right, sounds good. So what I might do is, I'm gonna keep moving for now. I'm fishing around for a spot where we reach like a natural pausing point. I think we'll try to push through one more page of notes and then we'll take a break. A little bit early for our break. Okay, so next is the measurement update step. Because everything we've really been seeing so far is just letting the physics play themselves out. But this is where we actually take a measurement into consideration. So we will begin with our measurement model, which should look extremely familiar after our lectures on estimation theory. So we have y with a hat on it is equal to hx plus nu, where nu is our measurement noise, and it is a Gaussian with zero mean and covariance R. That is our measurement covariance matrix. Well, really, this is our measurement noise covariance matrix, but what you'll see is because that's the only source of noise, it becomes the measurement covariance matrix, right? So just as a reminder, and we've seen this before, I believe, but to formalize it, the measurement covariance is, that's supposed to be the word covariance. Hope we can read that. Well, what is it? It's the expected value of our measurement minus the expected value of our measurement, and then all of that times itself transposed. Measurement minus expected value of measurement, transpose, and then close bracket. So if we think about it for a second, the expected value of the measurement is what? Well, I'm going to do a quick aside here. The expected value of y is going to be h times the expected value of x is just x, plus the expected value of nu is 0, so it's just hx. So what this becomes is the expected value of hx plus nu minus hx, hx plus nu minus hx. Transpose, well, that is just the expected value of nu transpose, and that's r. So in that way, our measurement noise covariance matrix becomes our measurement covariance matrix, because this noise is the only stochastic thing in this equation. So this is old news, but I just wanted to make sure that we understood this before we move on. So in this case, we will define, so we've talked about how x with a hat on it is the estimate of our state. That's the notation that we're using. I'm going to add that if there is a minus superscript, this is the estimate of our state before processing a measurement. So you can imagine a measurement comes in, okay? It's been, I'm just making something up. It's been 1 minute since the last measurement came in. So we now need to use our state and covariance propagation equations that we learned in lecture 22 and the beginning of lecture 23 to get us this, right? This is the result of our propagation. So you could think of this as a result of propagation. And you say, at this exact moment in time, this is what I think the state is before I consider my measurement. Okay? And then you can say that x hat plus is our estimate of our state after processing a measurement. And you can think of this as the result of our update. So this x hat plus is going to be what we move forward with. Okay. Now, if x hat is an unbiased, which we assume that it is, it's an unbiased estimate of our true state, which is without the hat, then we can describe error as E vector minus is equal to the true state minus x hat minus, and E hat plus is the true state minus x hat plus, where the expected value of E hat minus is the same as the expected value of E. I shouldn't be saying hat, that's just E minus and E plus. And that is 0, right? So we're expecting there to be 0 error. We're expecting that all of our noise sources will cancel each other out. We know that we're wrong about that, but we're kind of forced to say that this is our expectation because, you know, this is an unbiased estimator. Nothing should be throwing off our state estimate, right? That's critical, right? So then what we need, or what we will construct, and this equation here is really, this is where the magic happens. We construct a state update of the following form. Here it is. What is the relationship between x hat plus and x hat minus? Well, x hat plus is x hat minus plus some constant k, or I should not say constant, plus some value k times our residual. So residual is our measurement minus what our measurement should have been if we were right. So let's be abundantly clear about what each term here is, right? This term is basically our gut of the measurement. Okay. So you're saying, well, I've been driving for an hour. I've been doing 60 miles an hour. I'm pretty sure that we've driven for 60 miles. Therefore, our measurement should be blank. That's that. This is the actual measurement, which would mean that this entire term is your error, or we're going to use the word residual. So the residual is the difference between our measurement and what your gut would say. And then we say, okay, we're going to take that residual and we're going to multiply it by some gain, K. Start to think about like ModCon and control systems, right? That's our gain K. And then we add all of that to what our gut state was, and then this is our update. That's the idea. So you've got your gut, you've got your measurement, you've got your residual, and you've got some gain. I'm going to erase this because this is going to get a little bit, you know what, I might just leave it like that. I'm going to put the box around it, though, without the extra steps. So we'll kind of just squeeze this line through here. But this is super duper important. This is where the magic happens, right? This is the state update, or sorry, yeah, the state update equation. Put simply, this is the Kalman filter. It's this line. This is the CPU. This is kind of the core of everything that's going on, right? This is the Kalman filter. And you might be thinking, gosh, this doesn't seem that complicated. I mean, obviously, we just went through a whole bunch of equations on the state and covariance propagation, and those were pretty miserable and complicated. But this is pretty straightforward. Like, how is this so revolutionary? Well, the secret sauce is that letter K, the gain. That is by no means trivial. And Rudolf Kalman was the first one to sit down and say, well, what is the best possible value of K? Because we could just pick a gain K. We could just say, oh, I am going to pick the number 2 for my gain, and that this would still be a valid equation. Might not be the best idea, but you're not going to necessarily break anything doing that. But what Kalman came up with was a gain, and that letter K is not just any, it's because of Kalman, right? That's the idea. So that's going to become the Kalman gain, which will show a derivation just in a few minutes that the Kalman gain can be written as a function of other things, and ultimately that is your optimal estimator, right? You will never do better than that for a linear system of the type that we're working with. So this is the Kalman filter. The magic happens here. So all our work on propagation was dumb, or I'm going to use the word automatic. Not dumb as in a waste of time, although if you're feeling grouchy, you might think that it's dumb, but it is automatic, right? There's no thinking involved. There's no decision to be made in the entire propagate step. However, here, there is a decision to be made. And it all comes down to that gain K. So you could think of it this way. How much do we trust our estimate? How much weight do we give to our perceived error? All of that decision happens in this equation. All right, so we're not going to talk about the Kalman gain just yet. We'll get there. First, let's talk about this. how does our error change before and after our update? All right. Well, that's pretty straightforward, right? We already said that E plus is just X minus X hat plus, right? But X hat plus is all of this, right? So that makes this term X minus X hat minus gain times residual, right? But now isn't X minus X hat minus just E minus? So you can think of it this way. Oh, I apologize. I skipped a step here. This isn't just a regular X. This is an X hat minus. If anybody caught me, then kudos to you. All right. So what this is saying then is our error after our update is our error before our update minus, because our error should be getting smaller, I hope so, K times, okay, well, let's expand some things. Isn't X hat minus, well, let's think of it this way. Y is really HX plus nu minus H X hat minus. Okay, we're going to regroup our terms then. So this becomes E plus is equal to E minus K, and then H X minus X hat minus plus nu. But X minus X hat minus is E minus. Have that backward. There we go. All right. So then let's continue to kind of help things around here a little bit. So our next kind of iteration of this would be, okay, E hat is E hat minus K H E minus plus nu. And so finally, if you want to distribute and move some things around, we can say this. E plus is equal to identity matrix minus KH times E minus K times nu. Where, I'm going to scroll down a little bit. This, just to be abundantly clear, is error after update. And this, to be abundantly clear, is error before update. Right? So it's absolutely crucial. I mean, the error should be getting smaller. That's kind of the idea, right? So I minus KH. So that would mean that, you know, we're trying to make the error as small as possible afterwards. Now we can actually use this equation to help us with our covariance. So I want to do that, but I feel like this is a natural pausing point. So I'm going to stop right here. First of all, are there any questions about our measurement update step equations up to this point? There's still a lot more to go, but I think this is a good spot to stop. It's 6:52, but like really 6:53. So let's say we'll come back at 6:58. And I'll stick around over the break if you have any questions about our material today.
Paul,
Yes. What can I do for you?
this is related to the email that I sent you, but so what we're doing is essentially going to result in a discrete time Kalman filter, it sounds like.
Let's see, because it's going to be a Kalman filter where our so this is something that you're going to be implementing in MATLAB. Uh,
Hmm.
so this is where I'll reveal my ignorance. What do you mean by the difference between a discrete and a continuous time Kalman filter?
So like the discrete time Kalman filter is the most common one where you talk about, the measurement at step K versus the measurement at step K minus one, that sort of thing.
Yes. Yep,
And
that's the direction that we're headed.
okay,
Yep.
cool.
Good. So it sounds like your past experience is going to come back to help, which is going to be great. Um, I'm trying to imagine because I every time I've implemented something like this, it's always been, oh, at this, regular and kind of expected update time, we've got some new measurement to process, and
Mhm.
so in a continuous time case, would it not be like TK and TK minus one? Is that the idea? It's just kind of a general function of T?
I honestly, I've only done discrete time Kalman filters. That's the most common one. I
Okay.
don't think continuous times are done very often,
The
which is
most
why I
common
was
one?
initially confused.
Yeah, no, it sounds like we're talking the same language, basically.
Okay.
Yeah. And this is
Um,
where I'll be the first to admit, like, I am not a Kalman filter expert. Like, I'm somewhat well studied in it, but it's yeah, the odds that somebody in this class knows more than me is relatively high, and that might be you.
uh,
I'll
very
ask
much
you.
probably not. I've just implemented a bunch of them.
Okay,
But
well, I'll ask you to keep me honest if I say something that's overtly silly.
okay. I was worried because the what you said was the down and dirty method is very similar to what I've done. I was like,
Okay.
oh no.
Oh, I'm not trying to put you down. This was just the I haven't implemented enough common filters to have come up with my own opinions about what's a good idea and what's a bad idea. So this is kind of a uh, genetically acquired opinion from my professor. But yeah, that is the sort of thing which I think would probably work just fine over short time scales.
Hmm.
We're worried about like if your mission is like 2 months long or longer than that, that's the error is going to start to stack up, that sort of thing. Um, but I think for the homework assignment, you could probably get away with either method just fine. And similarly, we're about to see when we go through the update equations, there's a quick version and then kind of a better version of the covariance update. And
Hmm.
so you might be familiar with what is it, the Joseph form and does that sound familiar or maybe not?
Um, Not particularly, but again, I've done all discrete time.
Okay, yeah, we got a Joseph form and then a collapsed form of our covariance update equations. And well, you know what? You're supposed to be taking a break right now, so why don't I stop bothering you? You could. Oh no, it's 6:58. Oh crud. Okay, I was gonna be like, Renee, go enjoy yourself, but no, we done spent the time talking. Um, okay, but yes. So thank you for your clarifying question, though. I hope that that cleared things up a little bit. All right.
Thank you.
So that's that. Time to get back into it. So we have this equation, which is not super useful. Like, okay, we now have an estimate of how our error is going to improve, which is great. But ultimately, what we want is we have state and covariance propagate equations. We now want state and covariance update equations. Well, we've got our state update equation right here, right? This is it. This is where the magic happens. But there's a big question mark on that K, so we need to kind of double back and talk about that. But then also we need to talk about our covariance update equation, and we're going to do that right now. So how to update the covariance. All right. So you can think of it this way. P plus is equal to the expected value of X. Oh, I'm sorry. Not a hat. Apologies. Just a regular old arrow. So it's the true state minus the estimated state. In this case, it's the estimated state after the update, right? And then we've got true state minus estimated state after the update transpose. But in this case, isn't x minus x hat plus just E plus? So this is the expected value of our error, transpose. That's the idea. And now this is where we can substitute this equation into here. But won't that get really gross? Yeah, it sure will. That's where we're going. All right, so P equal to the expected value of, okay, it's going to be I minus KH times the old error minus K new. And then we have I minus KH times the old error minus K new transpose. Okay, great. And if we distribute this, so this is another FOIL operation, right? First, outer, inner, last, or you've got, A, B, A, D, A, C. You know what I'm trying to get across, right? You get a 2 by 2 and we're distributing. Getting myself tongue-tied over the letters, but you get the idea. This is going to be P plus is equal to the expected value of, scroll down a tiny bit here. All right, it's going to start as what? I minus KH E minus, and then E minus transpose I minus KH transpose. That's the first term. The second term is I minus KH E minus, and then we've got new transpose K transpose. Okay. Now, unless I'm mistaken, that is a negative sign. Okay, good. And then we've got another negative K new each. Oh, no, sorry. That is still a minus. But this is an E minus transpose. And then we've got I minus KH transpose. And then the final term is going to be plus K new transpose K transpose. So it's the expected value of all of that. All right. Not too terrible. Guess it could be worse. Now we're going to distribute the expected value operator into each of these terms. And remember, the expected value operator only cares about the things that are stochastic in nature, that have some random aspect to them. So this becomes, the first term is I minus KH expected value of E transpose times I minus KH transpose. Maybe we can already imagine how this is going to simplify. The next term is I minus KH expected value of E new transpose, K transpose, minus K expected value of new E transpose, I minus KH transpose, plus K expected value of new transpose, K transpose. Simple as can be, because now the expected value of E minus transpose, well, the expected value of E plus transpose is P plus, the covariance after the update. So this must be the covariance before the update, or P minus. Okay. The expected value of the error before we update the state and the noise in the measurement. Well, think about it. How does the noise in the measurement affect our propagated state? The measurement noise has nothing to do with our filter model. So these are uncorrelated. So this is 0. And then by that same logic, this is 0. Okay. And then the expected value of new transpose, we talked about this earlier in the lecture, that's just R. And so our covariance update equation becomes P plus is equal to I minus KH P minus I minus KH transpose plus K R K transpose. Nice and simple. And so this is the covariance update equation. Covariance and specifically, this is what's called the Joseph form. This is the Joseph form of the covariance update. So I'll write that out in English as well. This is the Joseph form of the covariance update equation. So compared to the simplified method, which we have yet to learn, this is more stable, meaning this equation can be trusted for longer, but it is also more computationally expensive. You can do it for cheaper if you really want to. All right. Now, this is also valid for any gain K. Once again, we have not enforced that K is the optimal gain K. We haven't even enforced that K is a good idea yet. These equations are more general than that. And finally, this enforces symmetry. There we are. All right. So now let's double back, because I'm sure you're all dying to know, where does the Kalman gain K come from? That's what we're going to spend most of the rest of lecture on. And if we have time for it, I'd like to go a little bit further, but this is very important that we get this right. So questions on the covariance update Joseph form? So far, so good? All right.
Can you scroll back up really quick?
Sure. Just let me know if that's far enough. Is that good enough or further?
That's good.
Okay, I'll pause here for a minute.
Thanks.
So what we're about to do then, maybe you can even imagine how this is going to go, right? We're going to find some Kalman gain K, which is the gain which minimizes our error, okay? Well, so what we're really saying is it minimizes the error after the update. Okay, so far so good. So what we really want to do is come up with some cost function, which is a scalar, which is a function of K, that we can then try to optimize. And when we optimize, we're thinking about first differential condition, we're thinking about, techniques from design optimization. Maybe we're even thinking about the matrix vector calculus that is awaiting us because we have an optimization problem. At this point, we've seen a handful of these sorts of problems in class, and there is absolutely matrix vector calculus on the horizon. So let's return our attention to the Kalman gain K. So we want K to minimize the mean square update error. All right. So min of jk, and that is not just kidding, it's j, the function of k, is the expected value of E transpose E. Okay, so what we're saying is the expected value of the sum of the squared error, so there's the mean squared error, you can think of it that way, after we've updated the state. That's what we're trying to minimize. Now, this is where we get to start being a little bit sneaky. So first, what we're going to do is we're going to shoehorn in the trace operator, because E transpose E, well, that's just any scalar, right? A transpose A is just the norm of that vector, right? It's going to basically be A squared in that case. So because we have a scalar, the trace of a scalar is just itself. So we're allowed to kind of shoehorn in the expected value of the trace of E transpose E plus, close, close. But remember that the trace operator is actually the same, even if you rearrange the order of the multiplication, as long as it's a cyclic permutation. So we could also just as easily say min j of k is equal to the expected value of the trace of E transpose. This is equally valid. Okay. Now, it's also the case that the trace is not a stochastic operation. So you can actually switch the order of operations here and get away with it. So really, you could think of it as min of j of k is the trace of the expected value of E transpose. Well, what is the expected value of E transpose, except we've basically just said that what we are trying to minimize is just the trace of our covariance. Which hopefully that makes some sense, right? The covariance is the matrix that describes our uncertainty in our measurement after we're done with our update. So you want that matrix to be small, as in low uncertainty. So what we're trying to do is minimize the uncertainty after we've made our update, or maximize the uncertainty gained by our, what is it? Minimizing the uncertainty or maximizing the certainty. You could think of it either way. But so this becomes our problem now, which is great because P is actually something that we know what it is, right? P plus, well, that depends on the equation. This is why we did things in this order. That depends on our Joseph form covariance update equation. So we're going to need this in a minute. Okay, so this is where we'll say, but P is a function of K. So we've got substitution to do. And one more hill to climb. Why do I say one more hill? Because actually we're almost done learning about regular old linear Kalman filters. Like we've been doing it for a while, and the end is in sight. Once we know the Kalman game, we kind of have everything else, right? So let's keep pushing. First, a few useful properties. So I'm going to label these because we're going to need them later. Number one, the derivative with respect to x of the trace of f times x is f transpose. Number two, the derivative with respect to x of the trace of f x transpose is equal to f. Oh, I'm sorry, this should have a 2 right here. And then number three, the derivative with respect to x of the trace of x f x transpose is equal to x f transpose plus xf. Okay, these come from where else? The matrix vector cookbook. Remember the matrix cookbook? We learned about that before. So what we can do then, we're going to need these in a minute. This might seem completely arbitrary that I've put these here, but this is sort of like getting your paints ready for your painting that you're about to do. So we are going to need all three of these to paint the picture that we're about to do. We can find K by applying what else? The first differential condition. All right. So from before, if we're trying to minimize the trace of P plus, so what we're really saying is the derivative with respect to K of our error function J of K, Well, that's the derivative with respect to k of the trace of p plus. Well, that's 0. That's what we're saying. The derivative with respect to k is 0. So let's make our substitution then. We're going to plug in this Joseph form equation for p plus. Okay, so what we're saying is the derivative with respect to k of the trace of I minus kh p minus I minus kh transpose plus kr k transpose is equal to 0. All right, I'm going to distribute because I think that this first term is really 4 terms, right? You've got I p kh transpose, kh pi, kh p kh transpose, right? So there's 4 terms in this first thing. So we're going to expand. And this is where I'm going to skip a step and apply the differential operator and the trace operator to each of the terms. Oh, never mind. I'm not going to skip a step. I skipped a step with my eyes when I was looking at my notes. But we're not doing that just yet. So this is the derivative of the trace of, okay, first term, p minus. Second term, p minus h transpose k transpose. Third term, kh p minus. Fourth term, and it's going to be a plus, kh p minus h transpose k transpose. Fifth term, k r k transpose, and this equals 0. All right, this is where we can start to split things up a little bit. So we've got the derivative of the trace of p minus, okay, and then we have minus the derivative of the trace of p minus h transpose k transpose, minus the derivative of the trace of kh p minus, plus the derivative of the trace of kh p minus h transpose k transpose, plus the derivative of the trace of kr k transpose equals 0. Simple as simplicity itself. Okay, great. So this is where I'll need a volunteer from the audience. Of course, every time we do one of these matrix vector calculus kind of steps, I always like it if I can get some assistance. So what I'm looking for is one term at a time. And you don't need to tell me what the solution is. Just tell me which one of these 3 properties we're going to use. So this is where, is there room for everything on one page? No, kind of not. Okay. Can I zoom out a little bit? Let's see. Is it? Yes. Okay. Nice. Zoom out a little bit. And I'll zoom back in because it's going to get confusing in a second. So we'll do one term at a time. Can somebody tell me what is the derivative with respect to k of the trace of p minus? I'll give you a hint. P minus, is that a function of k or no?
It's not a function of k, so then it just drops, correct?
Perfect. Very good. Yep. Excellent. So let me zoom back in. There we go. So this is just 0. Nice. All right. Second one. Now k is absolutely in there. It's going to be the derivative with respect to k of the trace of some stuff times k transpose. Which one of these does that look like?
It looks like number 2.
I like it. Number 2 sounds good to me. So number 2 is saying the derivative with respect to x of the trace of some stuff times x transpose is just the stuff. So in this case, what we would do is this whole term becomes minus EH transpose. And that's by rule of number 2, right? So this gets a little number 2 over top. All right, what about the third one? So we've got the derivative of the trace of k times some stuff. Which one is that?
It looks like number 1.
Number 1, I like it. So the derivative with respect to x of the trace of fx is f transpose. So in this case, what we would arrive at here is actually not not HP, but it's going to be P minus transpose H transpose, and that gets a minus sign. All right. Now, what I'm going to do here is I'm actually going to loop these into one term. Might seem a bit weird, but bear with me. This is really the derivative with respect to k of the trace of k, and then in parentheses, h p minus h transpose plus r k transpose. So we're just combining like terms because both of these start with k and then end in k transpose. So that's all we're doing. So, okay. So this is the derivative with respect to k of the trace of k times some stuff times k transpose. Looks an awful lot like number 3. And so what that would leave us with is k times the stuff transpose plus k times the stuff. That's the idea. So this, oh, I should mention this is number 1. Then by way of number 3, this becomes k times h p minus h transpose plus r quantity transpose plus k h p minus h transpose plus r. But what's neat is this term is symmetric because you've got h, p itself is a symmetric matrix, h transpose plus r also a symmetric matrix. This whole thing is symmetric. So if you transpose it, you've accomplished nothing. So we can actually simplify this tremendously. Similarly, this term and this term are actually the same thing because p times h transpose is the same as p transpose times h transpose because p is symmetric. So all of this becomes negative 2 p minus h transpose plus 2k, and then in parentheses, h p minus h transpose plus r equals 0. Okay. So what that means is we can move this over to the other side of the equal sign. And so we would get k times this stuff is equal to ph transpose. And then we can right multiply. So I'm going to skip a step. We're going to right multiply by the inverse of this. So if you'll permit me to skip a step, what this arrives us at is k is equal to p h transpose h p h transpose plus r quantity inverse. And this is Rudolf Kalman's gift to the world. This is the Kalman gain. It is guaranteed to minimize your uncertainty or your money back. Right? This is the k that we plug into our state update equation, but it's also the k that we plug into our covariance update equation. So this is going to be absolutely critical. It'll permit me to scroll away for a second, all the way back up to when we learned how to update the state, right? So I should really label this with state update. We mentioned that k is going to be doing the heavy lifting in this equation. And then when we learned how to do the covariance update, the Joseph form, k features prominently in there as well. Well, here is what it is. And so you can imagine an algorithm coming together from this, where with each new measurement, we know h because we put together a measurement model. We know r because we have an idea of the uncertainty in our measurements. We have p, which was propagated. So we go back to what we learned in lecture 22 to do our covariance propagation. We compute k, our Kalman gain, and then we use that to do a state and covariance update. And then the whole thing just keeps on turning. All the wheels keep moving, right? That's the idea. So this is our Kalman gain. And at the risk of overstaying my welcome and keeping talking after the usual time, if we keep pushing for 5 more minutes, we reach a really nice natural stopping point. And we've already met the minimums. Like we now know how a Kalman filter works. But we are going to go through one more simplified version of the covariance update if the Joseph form wasn't to your liking. And then I have a massive flow chart that basically explains the entire Kalman filter in one figure. But I think what I'd rather do is start with that on the next lecture and just let you all out of here. So questions on the Kalman gain? Otherwise, we're going to keep moving. We've got one last topic to discuss. So if desired, we may develop a compact form of covariance update. So the basic idea is the covariance update equation, the Joseph form, has K in it. Why not just plug in this equation for K and see if we can't simplify some things? And that's what we're going to do. So in this case, we start with P plus is equal to I minus KH P I minus KH transpose plus KR K transpose. Or if we feel like distributing, this becomes P plus is equal to P minus minus P minus H transpose K transpose minus KH P minus plus K H P minus H transpose plus R A transpose, right? This is not news. This is the same thing that we saw before when we were doing our Kalman gain derivation. Now what we're going to do is plug in. So we're plugging in the Kalman gain equation selectively. So what I mean is not every term. Sometimes we're going to leave K alone. Sometimes we're going to plug in. And hopefully it's going to be clear why in a second. So then this equation is P plus is equal to P minus minus P minus H transpose K transpose. So we're leaving that one alone. Minus KH P minus plus, now we're going to start plugging in P minus H transpose. So we're plugging in for the first K already. We're plugging in for this K here. P minus H transpose H P minus H transpose plus R inverse H P minus H transpose plus R H P minus H transpose plus R inverse H P transpose. So this term here, scroll down a little bit. This term here and this term here used to be K. Otherwise, we have the same equation as the line above us. But the thing is, this is just something inverse times something, right? You've got a matrix times its own inverse. So this is just the identity. Okay, so then bear with me because things are going to get a little bit cooler in a minute here. So this becomes P plus is equal to P minus minus P minus H transpose K transpose minus, okay, now I'm going to plug in for this K. So this is going to become P minus H transpose H P H transpose plus R. Okay. And then we have inverse H P. All right, and then our last term, which is going to be P H transpose H P H transpose plus R inverse H P minus transpose. What you'll notice is that this term expanded and this term are positive and negative of the same thing. So this becomes 0. So this simplifies a huge amount. And what we're left with is just this. P plus is equal to P minus P minus H transpose K transpose. Or if we want to rearrange things to make them look a little bit cleaner, P plus is equal to I minus K H P minus. Okay, so what this is a collapsed form of the same equation. So it's easier to code up, although I kind of liked the other form of the equation just fine. This isn't really buying you very much. Collapsed form of the covariance update. So I want to be abundantly clear that while this is simpler, this is not recommended. It does not guarantee symmetry. And it invites numerical issues. But I want you to be aware of it in case you decide that that's what you want to do for your homework. So just to then summarize, because like we're done, that's all the content for today's lecture. We now know how a state and a covariance, and really the covariance is actually the star of the show here. We don't care as much about the state as we care about how uncertain we are. That's actually like the main point of the Kalman filter. The covariance is kind of the unlikely sidekick, which turns out to be the main character, right? So we really care about our uncertainty in our state, which is what we're trying to track. We now know how to propagate those things over time using our physics model. And then we know how to update those when a new measurement comes in. And the star of the show when it comes to the update is the Kalman gain. This is where the magic happens. This is the razzle dazzle, because you can compute the Kalman gain and we can use that for the Joseph form or the collapsed form of the covariance update and the state update. And it's not just any gain, it is the gain which is guaranteed to minimize your error or to minimize your uncertainty. And that's about it. So this concludes not only today's lecture, but our discussion of linear Kalman filters. You'll notice I say linear Kalman filters. There's 2 more lectures in this unit. So we have a lecture coming up on various kind of asterisk and you should be aware of this and kind of Kalman filter considerations. That's going to be our next lecture. And then our final lecture is actually what we're going to need for the homework assignment. You might even have started peeking at homework 5 already. In homework 5, we're going to be propagating something, but it is not linear at all. It is a super not linear measurement model, and it is a super not linear state update or a state propagation model. And so given that, we then need some like booster pack, some sort of improvement on the Kalman filter such that it can handle nonlinear measurements and nonlinear state dynamics. And that's what's referred to as an extended Kalman filter, which is one of the most commonly used filters in practice today. So one thing at a time. That concludes our discussion today. I will stick around to answer any questions, but otherwise class is dismissed and hope you all have a good rest of your day.